So, hello everyone, welcome back to Knowledge Culture. Uh, Today we have our lecture 3, I guess. It is on optimization. Here's a PPT through which we will be going today. Right, I'm gonna wait for like 3 minutes. We are going to start at 3:30 exact. Before we start our session at 3:30, first, I would like to tell you what we are doing. We are doing optimization, of course, to the lecture 3 of artificial intelligence with Python in our live session course, right? Yesterday, we did our probability, our uncertainty lecture 2 it was, right? If you guys could not join yesterday for some reason, you can still go and watch the uncertainty lecture after the session. Of course, this session I think will get over till 5:30. So today's session is well different from optimization. I mean from uh, uncertainty, but till now we were doing like too much like mathematic questions or like algorithms. Today we also have many algorithms, but today is like today will be like much easier for you to comprehend. I think so, because you see, this is all theory based, and we will be diving more into Python than getting into different algorithms. It is not like different inference. It is not like different inference rules and different probability rules like negation, marginalization, or like conditioning or like inference rules also. Right? So, hello, yeah, welcome. We are going to start in like 1 minute. So, and today's lecture 3, optimization. It is divided into 3 parts. First is our search. If you know search, like it was our lecture 0 search, but today is a little different. It is like local search. It is like search algorithm that maintains a single node. I will tell you what is search in a minute. And then the second part is programming, and third is constraints. The programming one is like linear programming, like mathematics. How do we solve different mathematics in optimizing and things like and constraint. We will be learning CSP, uh, that is constraint satisfaction, right? So I guess we should start. So first of all, what is optimization? Optimization is choosing the best option from a set of options. We have been talking a lot about optimization since our lecture 0, that was our search. How did we do that in lecture 0? In search, we in the search algorithms we did like we had maintained the path cost, and we were trying to get the path cost lower, and down. Then in knowledge, optimizing the and minimax and all, uh, so that our computation did not take that much time. That was optimization for us. And then in probability optimization, there were not that we did not talk about optimization that much probability, but the most important optimization we talked about in probability was in that we did sampling, right? So sampling in like that was approximate inference instead of enumeration. That was exact. We did sampling, and then we did rejection sampling, and then we corrected our rejection sampling. The problem there was with rejection sampling. Uh, like by fixing the node, by fixing r, time, our train that it is our time, right? So today we will be learning optimization and different things like local search, linear programming, and constraint satisfaction problems. So uh, we there are numerous ways of solving these problems which we will be looking at. But what we want is the best way of doing it, right? We want things to happen fast and effective, like so that like optimized, right? So first thing, the first part of today's lecture is local search. I will give you 3 minutes break after each part. Okay. So first is local search. Local search is different from a search algorithm because local search is the search algorithm that maintains a single node and searches by moving to a neighboring node. Uh, um, we'll get to house and hospitals. Like what is the difference from the search? In search, we wanted a path, right? We like in maze solving or like going from point A to point B, right? But here, uh, we do not care about the path. We care about the solution. Uh, we do not. We care about solution to get a goal, not the specific maze path, right? That is local search. Like we are setting up a planned city where should be the hospitals, right? They should be near the houses uh, and all. So we do not care about the path, we care about the setup where they should be finally, right? So that is local search, they come under local search. Let us look into this houses and hospitals example. uh, Imagine that we have some houses. We have some houses. We start with four houses, and we have to put two hospitals, and so that path our cost is less, right? They should be near the house, and it should not be like it is close to one house but far from another house, right? So the total for that we do the total uh, distance from the house for both the hospital from all the four houses. We merge them, and that comes out with the cost. We are trying to minimize that cost. Okay. So uh, um, so here it is written, place two hospitals to minimize total distance from every house to its nearest hospital, correct? And then each arrangement of hospitals is a state. Yes, there are different states. We are trying to find the best state here, the optimal state, the optimal placement of the hospitals. So we are trying to find the optimal state of the hospitals, uh, and that optimal state is also that optimal state we are trying to find. So the goal is to find that lowest cost one, right? So the cost here we will calculate through Manhattan distance. Manhattan distance we discussed in search lecture 0, right? So that means only horizontal and vertical movements count, no diagonally. And some distance from each house to its nearest hospital. Now let me show you the example. I got the image right here. Uh, Wait a second. Hmm. So here it is. Like we take random houses placement like this four, and we place two. We place two. Not this one first. Let's do this one. That was the optimal one. So we have two houses, four houses, and we randomly place the hospital in this state. Okay, and right now the cost comes out to be 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Right? No diagonally, no nothing. Okay. Cost is 17, and this is one of the state. We want the uh, right now we want the optimal state, right? So this is one. Okay. uh, yeah. Why is it not selecting here? So not this one, I guess. Oh man. hmm we want. Okay, open. Let me open that, guys. uh, I guess it has closed. uh, so we want this one here, right? The 17 one. So let me close this. We have two of the same one open, I guess, right? So we close the image test one. Yeah, here. So we this is one of the state, right? This is one of the state. It's not working, I guess. That's not working, right? Okay, so this is one of the state. uh, yeah. Yeah, now it is working. So this is one of the state, and we want the optimal state. So we can like keep this stagnant and then move this hospital this side, or like this side. That will be changing a state. It will be a new state. We cannot go diagonally, right? So where do you think we should move this hospital? Um, we can try moving it here, right? We can try moving it here, and then because you see it is then only 3 away from here and 3 away from here, so our path cost will go down 2. Our cost will go down 2, and then we have to move this house, and then like to here, and then maybe here, right? And then we will end up with this, right? We will end up this with this. And yeah, this one is doing very pretty well. The cost comes out to be 11. uh, so this is nice. This is nice. Okay, so our goal was to minimize path costs. Our cost has gone down. So let us have a look at what we were actually doing. Yeah, so there's we have a space like this. These are two diagrams, guys. Let me create the line between those. So they are separate, guys. So uh, this is like a state space. These vertical bars, they represent a state. So each of the time we move a hospital, we are in a new state. So if we are trying to minimize, we want the this one, right? This seems to be the lowest, right? So this is the space landscape, and height represent the cost of the state. Okay, the height represent the cost. So this one is the maximum. So all these bars are configuration of state. So now we may want the maximum value, that is the global maximum. For that we use this objective function. uh, Objective function, okay. And and sometimes we may want uh, we may want the lowest, we may want the minimum, which is called the global minimum, which is called the global minimum. Okay, so this one is a global minimum, right? So uh, the global minimum uses cost function. uh, it will use cost function, right? Maximum one was using objective function, run straight into this. If we run the state into that function, and find which one will meet that objective, right? And for cost function, we with cost function we find the state with the lowest cost. Now, how to find the global maximum and global minimum? So we are like in a state. Okay, there is the objective function, there is the cost function. Then let us first see these terms. Okay, so these were the algorithms to maximize this value, that value, and cost function to minimize that value. So what is current state? Current state is like the state in which we are right now, and the state which we are examining right now, which we are examining right now. So we move from our current, then we move from current state to the state to our right or to our left, right? Like we are using the objective function, so we need the maximum. So right now is our this is our current state, okay? And these two are our neighbors. These two are our neighbors, okay? So we in local search, we do not look at them, we go into them. Okay, we move from our current state to this state, and then we examine that. Okay, so we are using the objective function, we see that this neighbor is higher, we will come here, right? And how did we know to why to come to the state? We know that this one is higher, so so we had to come to the state, and then we see that because we were using the objective function, we see our neighbors now, which is this and this, it is lower than us. So I think we have found the maximum, right? We have found the maximum. So this thing which I just did, uh, go into our better state, is known as hill climbing. Local search moves from the current state to the neighbor, one step at a time. Unlike Minimax, it does not explore all states recursively. Yeah, we go one by one, step by step. We go to that state, we examine that. Not like Minimax. Okay, so now let me explain you Minimax. I mean, so hill climbing. Uh, let's take any of them. Yeah. So let's use hill climbing. Let's use hill climbing to find the global global minimum. Or let's find the global maximum. Okay. Don't focus on the local maxima right now. We will study that after hill climb. So this is not the global maximum, guys. This is just the boundary. Yeah. So let's say this is our current state. Which one I just colored yellow? That's our current state. Now we're trying to find the global maximum. What hill climbing will do is it will examine the highest neighbor. So out of this one and this one, it will choose this one because this one is higher, I guess. Yeah, it is higher. then the right one. So it will go left. Now this one is our current state. So out of this and this, it will of course choose this one. Then same for this and this now become our neighbor. It will choose this one because this one is higher. And then this one and this one is our neighbor. So we'll come into this one. And so then from for this for this one is our neighbor and this one is our neighbor, right? So this one is higher, so we will come into this green one, right? So for the green one, this one is the neighbor and this one is the neighbor, and both are worse. So it will never go to the worst one. We're trying to find the global maximum. It will go to the higher one, and if both are higher, uh, uh, if both are higher, it will choose highest of both of them. So it looks like we have found our global maximum, which comes out to be this green one because its neighbor are worse than it, right? And yeah, it looks like that we are correct, right? We can do the same for like global minimum. If you want me to do that, let's open global minimum one. This one. So let's say we started at this one. This is our current state. So we do not stay in the current state. We move. We This one is worse, so we come into this one. Out of this one and this one comes out of the worst, so we go to here, and then out of this one, then out of this one and this one, this green one comes out to be the worst, so we come to the green one, and now we cannot do any better. Both of the neighbors are better, are higher, so it means we are at the minimum, right? We will not go to higher one. We are doing global minimum. We are trying to reduce cost function. So yeah, so this one was our global minimum. Uh, Now let us get into the pseudocode for hill climbing. I hope you guys are liking the session. Uh, let us uh, let us get into the coding, a general code for implementing this algorithm. Let us hill climbing. This code you see above, that is from our previous lecture. This the Minimax code, that is for the min player. Okay, so let us write the code. It goes something like this. So the function hill dash climb, and then we give them the problem, then we examine our current state. If current equals so the current is the initial state of the problem, so we define it as the initial state of problem, and then we are going to start our function, our loop. Right, we are going to repeat this step again and again till we find our global maximum or global minimum which we want to find. So we are now defining, now we want like it go to our neighbor. So like we want the highest value neighbor, we are trying to find the global maximum, so we want the highest valued neighbor of current, okay, of our current state. This current state will keep changing, okay? And neighbor if neighbor not better, if both the neighbors are not better than current, not better than the current state, then then it means that we are already on our global maximum, right? We'll start from random place, remember that. Return current, and then we are going to put this return has to be inside, and then we're going to put current equals neighbor. Uh, this is if this is for the else part. We just use the if statement, no else statement. If statement is not right, then we just choose the highest one and we put that as our current state, because you see we go from one state to another state step by step. So this was for hill climbing global maximum. Let me write this: global maximum. But what if we are trying to find the global minimum? Then we want the uh, lowest valued neighbor. We will just change that to lowest. Okay, and this will become our global minimum. You see, our min tier function is different from the hill climb global minimum. Okay. Now there's one problem with now there is one problem with this, what do you say, hill climb. That problem is that we may even find a even better solution, a better solution than this. We may find a better solution, but not always the best solution. This is a better solution than this. 17 cost, 11 cost. This is better, but this is not still not the best. If you are maybe screaming behind the screen, we can do better. We just have to place this. We just have to place this hospital here, and we will have our cost function of 9. Why it is not there? That is because we have to move to a better neighbor to reach this place. So to reach here, we first have to come here and then go here. We just cannot go diagonally. But if we come here, if this hospital comes here, then our cost function will change. It will become worse. It will become worse, and we will never go to a worse neighbor, right? So we might get stuck in a place where neighbors are higher, and I stop, but if our neighbors are higher, I stop, but my neighbors are not the best, right? So uh, this state, so this state which we are in right now is actually not the global maximum, because we need this hospital to come here to become a cost function of 9, right? But if we want to come here, we first need to increase the cost by going to this worse state and then come into this better state. So we never explored this state, did we? No. So when we got stuck into this good place and it seemed like that that we have found the global maximum, even if it is not, like it seems like, because our neighbors are worse than us. uh, so that means we are at the local maxima. We are at the local maxima, that is here. You see this, like if we start here and we slowly go here, then here, and then here, finding the maximum. And then we see both of our neighbors, that is this one and this one, are worse than us. Then our hill climbing algorithm will stop, right? It will stop and it will come back with this state, it will return with this state. But that is not the best state, right? It is a better solution than this, but it is not the best solution, right? So that is the highest in that area. That its neighbors are smaller than it, but it's still not the highest, and its state is not the optimal, right? Same can be said for local minima. What is local minima? That is that uh, here. That is that these three blue ones, uh, the these are higher. These right and left, the neighbors are higher than the state. That state, if you are in that current state, and then you will stop there, right? Like you started here, like you started here, okay, here. Then you come here, then here, then here, and then here. What will happen? This state, this one, and this neighbor, both are higher than this blue one, right? This blue one in the middle. So it means that it must be the global minimum, but actually it is uh, the lowest in that area, but it is and it is lowest in that area, that is its neighbors are smaller than it, but it is still not the lowest in all state, in all the states present. It is not optimal because this one, which I am coloring, is the global minimum. But I got stuck here because my hill climbing function will not go into the worst one, right? So we never explored this. Like if we start from this place, we will come here, and then we will come here, then here, and then we will again get stuck. What if we start here? We will come here. This one is same, right? So we will come here, and then we are again stuck at the local minima. So that is the problem with hill climbing. Did you understand, guys? This is not that hard to understand, right? So now, therefore, the another issue that can occur, another issue that can occur is getting stuck at a shoulder or a flat local maximum. Just wait a second. What is a shoulder and a flat local maximum? Let us get back into our state space landscape. So this, you see, 1 2 3 4 5 6, these 6 states are equal. So if we start here, um, let's say the computer might get confused where to go. So but let's say it came to the right, and then again both the neighbors are equal. Let's say it again came to the right, both the neighbors are still equal. So it may get confused, right? It may get confused. So it means that so this thing, these 6 states which are together, this is the flat local maximum. So formally it is a big flat state where all neighbors, at least 2 states ahead, are same in the cost. So the computer may get confused. And then what is the shoulder? A shoulder is a small flat maximum where neighbors are same, like this, right? This is the shoulder. The neighbors are same, right? but it is smaller than a flat maximum. Okay, it is not two states ahead. Less than two states ahead, it is a shoulder. So a hill climbing algorithm, local search algorithm, may get confused here. Yeah, you're trying to understand, right? What is the problem? The problem which we are facing with, there are many problems which we are facing with our hill climb. We cannot go diagonally. We cannot go diagonally because we are, and we will not go diagonally too. But there is no way to get into this state where the hospital is here. That in which we could have had the cost of 9, right? So that is the problem. And another problem is getting stuck on a shoulder or a flat local maximum. So let me introduce you to some of the hill climbing variants which may solve some of the problems but not maybe all. So I'm going to use this board here to write theoretical stuff. So let us get into hill climbing variants. First, which we were doing is known as steepest ascent. Steepest ascent, in which we choose the highest value neighbor or the lowest value neighbor. So this one is like a greedy one, right? A greedy one. So this one we have already explored. So let us get into other variants. First, most famous one is stochastic. What is stochastic hill climb? It is choosing randomly from the higher neighbors. Like we will choose randomly. Choose the right one or choose the left one. Okay. We will choose randomly. Then we have got our first choice. So in this we choose the first higher value neighbor. Like right or left. I saw right first, so I will go to do right if it is higher. Like I'm right now talking about when we are finding global maximum. It is the exact opposite when we are doing global minimum. So that is self-explanatory. So when we are doing the global maximum, in the first choice one, like we looked right first. So if it is higher, I will go right. I did not even look at left. First choice. Okay, and then random restart. Random restart is very famous. Random restart. What is random restart? That is, we are going to conduct hill climb multiple times. When we get stuck, we will conduct from a random spot again, from a random current state again, and then we are going to keep track of those, and then we are going to come back with the best state. Okay, so we are going to do it multiple times. Then the last one is local beam search. What is it? Local beam search. In this we choose the k highest valued neighbors. Okay, and local beam search we choose the k high. We keep track of many high value neighbors, and then we choose the highest value neighbors. Okay, the k highest value neighbor. So we have seen 1, 2, 3, 4, 5 variants of hill climb. That is steepest ascent, stochastic, first choice, random restart, and local beam search. But they may solve one or two of the problems, but they still have one thing in common. That is, they will never choose the one which is worse than its current state. Never choose the worst than it is current state. But as we have seen, it may sometimes happen that we have to choose a worse state to get to a better state future on, right? So what do we do to solve this problem? Uh, to solve this problem, we have simulated annealing. let us get back into the PPT. Uh, hmm. So this was hill climb finding a local search, local global maxima already discussed, local global minima already discussed, and when if you want to take a look like this, these are also many states. These are many states, right? These are not vertical bars. And then when hill climbing stalls, that is flat local maximum and a shoulder already seen. Hill climbing variants we have already seen. Let's get into simulated annealing. Simulated annealing. You would have studied that in physics, right? In physics, in science, right? I don't know in chemistry, physics. In physics, I guess. So simulated annealing is like when the particles get separated and then you go randomly here and there, right? So similarly, uh, we are going to discuss simulated annealing. So these are four states of simulated annealing. We are also going to see the code of simulated annealing. It is going to be hard to write del to e. This is del to e. I think I can copy del to e. Okay. So before start seeing these four steps of simulated annealing, I will first give a basic definition of simulated annealing. Listen very carefully. Listen very carefully. Uh, Simulated annealing. Uh, Early on, when there is higher temperature, like when we do simulated annealing, we have a high temperature at the start. So we are more likely to accept our neighbors which are worse than the current state. We are going to take risks. Okay. Uh, and then later on, when the temperature gets lower slowly, uh, we are less likely to accept neighbors that are worse than current state. So we are going to start hot. Uh, we are going to start hot, and then we are going to get cool and settle. So I don't think so. This text is visible. Uh, uh, yeah. So we are going to start hot. So when temperature is high early on, the algorithm freely accepts bad moves, exploring the space widely to avoid getting trapped at a um, at a local minima or local maxima, right? And then uh, we are going to then pick a neighbor. Uh, so, uh, so each iteration selects a random neighbor. If it is better than del to e, uh, I have that written. Del to e upon t, del to e, if the neighbor is worse then del to e less than 0 is worse. That is if del to e is less than 0, uh, accept it with probability e, e and then raised to like del to e upon t, that is to calculate the probability. A more negative del to e means low acceptance odds, because we want to go into a worse state but not too much worse. So we need to calculate how much worse are we going to. So there's a way of accepting these bad moves too. So and then cool and settle. As temperature falls down slowly and slowly, the algorithm accepts fewer bad moves and becomes more conservative converging towards the final solution. uh, I hope you guys understood this. Let me sum this as annealing on. So at the start, when we start finding from the current state, at the start we will be more free to accept those bad moves like going to worst neighbor, right? And then we are going to calc if we get like both of get to our like local minima or local maxima, and we like have to pick and or something, pick a neighbor. So we need to calculate how bad a neighbor is, right? We are never going to, so we are not, if it is better than del to e less than 0, if it is not, if it is less than 0, then we are less likely to do that. If it is like still positive, then we are more likely to accept that bad move. It is always accepted as a new current state, right? It's always accepted as a new current state. And then accepting bad move, I already told you, we have to accept it with the probability of e raised to like del to e divided by t, the temperature. And then negative del to e means lower acceptance odds, of course. And then as the temperature goes down slowly and slowly, when we are have explored much more of the landscape space, right? Space, uh, state space landscape. Then we are uh, more likely to accept fewer bad moves, and then we are going to converge to find a solution. Okay, so this was basically annealing. So let us get into the so let us get into the code of annealing. Okay, code is not written here. I will add the code for you. Don't worry. The code goes like this. This is for uh, simulated annealing. This is a physics, I guess. Mm. So I will be writing for maximum. Okay, let me write the code. Listen to this very carefully. Again, over there, sharp. Yeah. So again, function, simulator annealing. And then we are going to give in the problem and the max, because we need to tell him how many bad moves are we going to accept, right? And when are we going to start with accepting the bad moves? At the start, of course. uh, so current equals initial state again, initial state of problem. I can copy it. I can copy it from here. Work smart, not hard. Well, you should work hard too. You should know the basics before you get into something. Yeah. So then, I'm going to start a loop again. For loop. I hope you guys know for loop. Very basic. For t equals 1 to max. So that we are. This is for accepting bad moves. Okay. Bad moves. So now we are going to define the temperature equals temperature and then neighbor equals random neighbor. We are going, because we are choosing more randomly at the start because our temperature is high. It will be of course calculated. Neighbor equals random neighbor Okay, random neighbor, and then we need to calculate, right? Now let us get into that accepting bad moves and that. So picking a neighbor. So how do I write del to e? I think I have to go and copy somehow the PPT. Del to e. Control C. Control V. Yeah, del to e. So del to e equals uh, how much better our neighbor is. You want to calculate, right? How much better our neighbor is, because we will some bad moves, but not too much bad moves, right? Uh, yeah. Then if del to e, I will just control V. Uh, if del to e is less than 0, uh, that is, it is in negative, then you must remember that we are not going to accept it. So if that happens, our current will become neighbor, and if it is bigger than 0, the current will, of course, uh, uh, with probability, of course I have to write now, with probability, e raised to control V, oh man, oh, del to e divided by t, set current equal neighbor. So this was our code for simulated annealing. This is how we are going to frame the simulated annealing part of the code, of course. Uh, so I hope you guys understood the code. That is basically what I just told you in this slide. Okay. So how much? So thank you. So it's been 53 minutes, guys, and now we are reaching traveling salesman. Traveling salesman is the last thing which we are going to do before a 3 minutes break for the second part of this lecture. Traveling salesman. So let me first define you this traveling salesman. It is a very classic problem. So it is used in like deliveries and apps, like when you deliver some things. So what basically is it? So uh, we want to start somewhere, and then we want to go somewhere, like delivering our products and all, and then we want to end up back to where we started from. Like we start from here, then we come to here, then here, then let's say we went to here first, and then let's say we went to here, and then let's say we went to here, and then here, and then we came back to where we started from. Okay, traveling salesman, very classic problem. Now we want to do efficient. We want an efficient route and so that it saves time and fuel and all too. So how I'm only going to tell you how does that work. I'm not going to get into the algorithms. What we will do is like we are going. How do we first see the neighbor? What is a neighbor? Neighbor is what it is connected to. I mean, now we need to connect it to the ones which it is not connected to. Like this one, it is not connected to this one. So we are going to uh, remove this and for this too, and this one too. Right now, they somehow ended up to be intersecting. Hmm. And then we are going to put arrow here, and then we are going to switch these arrows, and then we are going to form an arrow here. And from this you can see like yeah, this state actually looks better than what we had before, right? It looks better. So it means we have saved some fuel and all. So we are like this. We are going to get. This is actually very 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 hard, and this is actually known as the NP problem. There is no solution. Uh, there is no actually no algorithm or solution to do this properly. Actually, to do this, no real way of doing this properly. There are many possible routes. Like you can see here, how many? Like hundreds of thousands of possible routes. So it is a very exhaustive search and is computationally prohibitive. So a neighbor state swaps two route segments, and simulated annealing finds a near optimal route at a fraction of the cost. Little bit. Of course, we are doing like 100 times. We are doing it instead of like 300,000 of time. So it is like a fraction. It will take a fraction of cost. So this was basically the traveling salesman problem. You see, this one is not optimal. If we want to find the optimal, we need to switch some paths, to perform simulator annealing or like switch neighbors, swap to route segments and all, and then try to find some better solution. There is no proper way of doing this, but still, this type of problems occur. So we have some things like some small things to do, like which I just described to you, to get a little near optimal route, right? So we need the shorter distance possible. Uh, Now we come at the linear programming problem. I don't know, the image is not loading. I guess it is not needed. So you guys will get a 3 minutes break. Uh, a 3 minutes break before we start linear programming. Linear programming is super short. Only one thing is there actually. But yeah, I guess uh, we have been here for like an hour now. 3 minutes break, and then we are going to get into constraint satisfaction problems, and then we are going to finish this lecture. Very fruitful because optimization is very much needed. 3 minutes breaks. 3 minutes break, guys. Go and drink some water. So yeah, if you remember yesterday's session, if you have not, of course, if you have not joined yesterday, you can go and see it. Or like I'm using a lot of search algorithms, and we are talking about like minimax and all. If you are interested in that, you can go and look at that after this. So yeah, today's session was not that hard. It's not that hard. You can see it is just about local maximum optimizing some path. We have already discussed so many things, so many algorithms. We're trying to optimize different categories, problems, categories. Now we're getting into the second category, right? The linear programming problems. So, in 1 minute, I'm going to explain you the problem structure. In linear programming, let me just have a look at the PPT till then. This is a programming example. We are going to have a look at this, and then this is the code, because it is not that easy for us to calculate this. It is not easy for us to calculate this. So we are not going to calculate that. I'm just going to explain you how to frame that. So any question that can be framed in this way comes into like a linear programming one. This is a worked example. Program structure we have here: cost function, constraint forms, individual bounds, and algorithms. Algorithms, we are going to look at the code. Just here. It is visible, guys. Is it visible? I'm going to change the text font color next time. Okay, it is 27. So let us start. Thank you for the support, guys. Let us start. So linear programming. So let us look into this linear problems. We are going to have we are going to have this one coefficient, and we are not going to have any squares or roots or like cubes, because those are not linear. So they need to come under the structure to solve uh, the problem. The structure, if this is not visible, I'm going to write it for you here. So heading first, of course, check out your notebooks. You can write this. We have never ever talked about having a notebook and writing all this in it, but you should have a notebook so that you can have a look at it later, like when you're outside. So first is cost function, something which we are trying to find, and we are trying to minimize. So like we have to frame it like in cost for one for running it for some time or like that. C2x2, it is like multiplying, and can go like till cn into xn, right? So we are trying to minimize the cost function, of course, and then we are going to talk about another structure, that is constraints. There are usually some constraints that bound our decisions, right? So constraints are form like constraint 1 for that, a2 into x2 plus like an xn, and then the constraint can be like it should be less than or equal to some value, right? The cost should be less than equal to this or something, or the time should be less than equal to this b, and then with bounds for each variable. Yeah, there are bounds for each variable. So let us look at the bounds for each variable. It can be like less than equal to xi, and then less than equal to ui, that it has to be less than this, it has to be less than this. Like we have to, let's look, have a look at the ppt. Yes, we have individual bounds, limits on each variable independently. Example, a variable cannot be negative or something like that. Or cost function I told you, like where xi has an associated cost with ci, c1, and then linear inequalities or equality bounding the variables which are most likely present, and then so these are solved using some algorithms like simplex and interior point methods. The code can in Python can be like CPU optimized or line out. We are going to have a look at it, but before that, let us have a look at the work example. I'm going to dictate you a question, and then we are going to frame it in this structure. Let's not have a look at the structure, and now let us look at the question. Not going to write the question. The question is lengthy. So here, very very carefully, and let me write that I'm writing a question of linear programming. Remember the handwriting. Let's ask the question. So two machines x1 and x2. There are two machines x1 and x2. X1, uh, take the notebooks and write that because you will not be able to remember the whole question. So there are two machines x1 and x2. X1 costs $50 per hour to run, and x2 costs $80 per hour to run. Okay, so there are two machines x1 and x2. X1 costs $50 per hour to run, and x2 costs $80 per hour to run. And then our goal is to minimize the cost. Okay, now here the constraint. X1 requires 5 units of labor to run per hour, and x2 requires 2 units of labor per hour, and it has to be, and we have a total of 20 units of labor. So it has to be less than 20 or equal to 20 units of labor to spend, right? And then x1 produces 10 units of output per hour. So this is the second constraint. Okay, listen carefully. X1 produces 10 units of output per hour, and x2 produces 12 units of output per hour, and the company needs 90 units of output. Okay, so let me repeat in one go. There are two machines x1 and x2. X1 costs $50 per hour to run, and x2 costs $80 per hour to run. Goal is to minimize the cost. X1 requires 5 units of labor per hour, and x2 requires 2 units of labor per hour. Total cost of 20 units of labor to spend, and x1 produces 10 units of output per hour, and x2 produces 12 units of output per hour. And the company needs like 90 units of output. I hope you guys got the question. Right. Now, let me frame this. Let us frame this in a linear form. So in linear form, there's no bounds. Okay, in linear form. So first we had our cost function. I'm going to wait a second for you guys to understand, to think what must be the cost function. Well, if you wrote in your notebooks or screen behind the screen, that it is 50 into some r plus 80 into some r, then you are correct, right? And then let us have a look at our constraints. Think of the constraints. I'm giving you a second again. If you said 5 units of labor per hour plus 2 units of labor per hour should be less than equal to 20 units of labor, then you are correct. Then let us have a look at our constraint 2. If you said 10 x plus 12 x2, 10 units of output per hour plus 12 units of output per hour, and this, then you are correct. If you put a greater than sign, then it would be incorrect. because we said we need 90 units of units per hour, so it could be less, right? We do not want too much, right? We do not want overflowing. Overflowing is bad. So but to solve this we want the greater than sign. So for that we are going to multiply it with negative 1. So if you somehow calculate it further and said minus 10 units per hour plus minus 12 units per hour greater than equal to minus 90, then you will be correct. You can comment down below in the chat, live chat, or if you are watching later, then comment down if you were correct. Okay, thank you, thank you. Uh, yeah, so this is how if we are able to frame this into this type of cost function constraints and all, then we are able to solve it using linear programming. Let us have a look at solving it using code. Yeah, I have zoomed in for you guys. So this is what we had. So result equals skippy dot optimize dot line proc. If you want to know what line proc is, line proc minimizes the cost by default. To maximize, we need to negate the cost coefficient before passing them in, and then because of course we want to do the best, right? And then we have got the 50, 80, and then we have got the like 50 units and 80 units. We have already told. I mean $50, $80, which we are trying to minimize, and then we got the upper bound, which is 5 units, and then A, U, B, and B. You define the inequality constraints, yes, and to express multiply both sides by, yes, I will told you. Result of success, of course, very easy. So upper bound 5, 12, 5 units, 12, 5 units of labor, 2 units of labor, minus 10 output, minus 12 output, and then what we want to achieve is 20 and minus 90, and it is of course less greater than equal to sign. We do not need to tell it. Yeah. Then and then if result dot success, then we're going to print it out like how many hours for x1 and how many hours for x2, and if we are not able to frame this properly, and if we are not able to calculate this, then we are going to print no solution. Well, we will be able to answer this question. The answer is not written here, but I actually know the answer. Let me tell you. The answer will come out to be for machine x1, it will come out to be 1.5 hours, and for x2, machine x2, it will come out to be 6.25 hours. Maybe it could have been better, maybe it could have not, but this was the answer that came when I run that in my local computer. You can check it out on your end when you will do it at your end, code this at your end. Now you understand this. So this was linear programming. We are not going to solve it on our own or with the computer, because it is very easy for the computer. And then we are coming at the last section of our today's lecture. It is constraint satisfaction. It is my favorite part. And this one will have some time, it will take some time. We are at 1 minute, 1 hour, 14 minutes, 15 minutes, you can say. I'll explain linear programming in 15 minutes. No break needed, guys. Let us get into constraint satisfaction problems. I will give you 1 second to brace yourself. So we already used the library Skippy and we used the algorithm simplex and interior point in the linear programming. Here we imported the Skippy. Yeah, we imported from Skippy. Sorry. Now we are going to get into constraint satisfaction problem. Before we go into our today's major example, we are going to discuss some constraint satisfaction. Three core components. Those are variables, domains, and constraints. All of them are very important. I'm going to come in a second. Uh, I'm coming in a second, guys. Yes, guys, I'm back. So yeah, you had that 20-second break. Cool of me, right? So, variables, domains, and constraints. For variables, what is variable? A set of unknowns to assign values to, like in Sudoku. Yeah, we can take an example of Sudoku. That is a different example. For explaining you these three core components, I'm going to use the example of Sudoku. Let me find a Sudoku online. Image, Sudoku image. I hope you can see this. It is like a 3 by 3 graph, right? It is a 3 by 3 graph in which we have to fill 1 to 9 numbers, and then no number should be same in the line, in the box, right? No numbers should repeat in the line, in the box. So the variables is a set of unknowns to assign, and so each empty square is a variable. You have to assign a value to it. Those values are stored in the domain. Each variable has a domain of possible values. It could be in Sudoku it is like 1 to 9. That the box would have 1 or 2 or 3 or 9 or 4, 5, 6, 7, 8. Yeah. But with the constraints Sudokus, which you guys know, we need to define them, the constraints, like in Sudoku, no two squares in a row, column, or box can share a value. So those are constraints, right? This is the main example which we are going to have a look at today. So, example schedule as a CSP. CSP stands for constraint satisfaction problems. So, 4 students can take 3 courses from A to G. Exams must fall on Monday, Tuesday, or Wednesday, with no student sitting 2 exams on the same day. And each course is a variable, right? Each course is a variable. And the schedule is valid when all constraints are satisfied. So variables are the courses, the domains are Monday, Tuesday, Wednesday, on which the courses exam can take place, and the constraints are that shared student courses must be on different days. So let us have a look at this. Child 1 took A, B, C, D. I mean, that is already written, right? No need to write again. So we will we will point a graph like this. Uh, don't confuse this graph with the search algorithm, but right. And D E, let's say C F and G, and then this is A B C D E F and G. These lines represent the constraints that A and B cannot have exam on the same day. B and C cannot have the exam on the same day. A and C cannot have the exam on the same day. B and D cannot have the exam on the same day. B and E cannot have the exam on the same day. D and E cannot have the exam on the same day. E and C cannot have the exam on the same day. E and F cannot have the exam on the same day. And E and G cannot have the exam on the same day. C and F cannot have the exam on the same day. And F and G cannot have the exam on the same day. Okay? With the constraints given here, we have defined everything. So this was the order, right? A, B, C, B, C, D, C, D, E, E, F, G. So now everything is set. Set of variables I have already told you, the domain values can take on I have already told you, and the set of constraint I have already told you. So before going ahead, there are two type of constraints. Constraints. First is the hard constraint, and second is known as a soft constraint. In this lecture, we are going to have a look at the hard constraint only. Hard constraint is a must. They must happen. They must meet. They must happen to meet the correct solution. And soft is like preference. We want most of the preference to take place, but sometimes we can have an exception. And then inside constraints, we have to inside hard and soft constraints, we have unary and binary constraints. How do they look like? Binary constraints. Unary constraint looks like that A course cannot have the exam on Monday, so we have only one variable here, A. This is a domain value, not a variable. Okay, so we have only one unary, and binary can be like A and B cannot have exam on the same day, right? Like that. So these are like constraints, hard, soft. Inside them we have unary, binary constraints. Now, when all the unary constraints are followed in a graph that I have made, in a graph like this, if all the unary constraints are followed, then it is said to be node consistent. Node consistent. What is node consistent? When all the values in a variable's domain satisfy unary contrast of that variable. And when like, let me give you an example. Let me create a small one in which we only have two courses, A and B, and let me list the domain value: Monday, Tuesday, Wednesday. And for this we also have Monday, Tuesday and Wednesday. Okay, now let me list some constraints. A equals is A not equals Monday. B not equals Tuesday, B not equals Monday, and A not equals B. So then let us start with node consistency. We want this node consistent. We are node consistent. So we take the first one, and A not equals Monday, so we remove it from the domain. Then B not equals Tuesday, so we remove it from the domain. Then B not equals Monday, we remove it from the constraint. I mean from the domain. Now all the unary ones, we are not look at this one right now. This is the binary one. All unary one are done. So now this is node consistent. We can say, right? Now another thing which I want to introduce is arc consistency. Arc consistency. What is arc consistency? When binary when binary constraints when binary constraints are followed. Okay, when binary constraints are followed. Okay, like if we want to make this binary constraint, I'm going to tell you how to do that, but it will be much easier when you learn the formal definition of arc consistency. That goes something like this, that same as node, but okay, something consistent, something which is same as node but now binary, to make the x r, and consistent to respect with respect to y. We need to remove element from y's domain until every choice for x has a possible value for y. You would not understand that in one go. Let me explain you with that example. So every choice I take for A, there should be some possible choice that I can take in B. Okay. For example, I remove uh, B. I mean from A's value, I set it as Tuesday. Okay. If I set it as Tuesday, then Wednesday is here, so I can set Wednesday. And then no, Wednesday and Tuesday not needed. Done. Both of them follow all of the constraints. Okay. But now the thing is, if this was correct. If if I would have chosen Wednesday for A, okay, now I have chosen Wednesday for A, and now I cannot choose Wednesday for B because A not equals B, right? So now I have no value for B to choose from. So that means it is not arc consistent. So this has to be uh, so this has to be Tuesday, and this has to be Wednesday and now we can say it is node consistent plus arc consistent. Consistent. Understood, guys? Now let us have a look for arc consistency, at the pseudocode for arc consistency. Right. First, we are going to have a look at the pseudocode for arc consistency when there are only two variables A and B. Okay. Okay. So arc consistency, and the first everything is working well. Because everything is working well. Chat, you were responsive. Thank you, you are responsive, guys. Uh, Now everything we have seen. Yeah. Now let us get into the code. The code looks like this. It is arc consistency wise, not art consistency. So function revise. We are going to revise it again and again. Have I introduced you to backtracking? I've not introduced you guys to backtracking till now. Okay, I will introduce you guys to backtracking in a second. Uh, uh, Backtracking I will introduce you to in a second. Firstly, let us look at the code. So, function revise CSP comma x comma y. If revised comes out to be false, revise equals false, then we are going to return. Then for x in x's domain. Now for x and x's domain, if no y in y's domain satisfies constraint for xy, for x comma y, then it means that we have chosen wrong, of course. So we are going to delete x from x's domain and then revised equals true, and then at last we are going to return with the revised. Return revised. It is not that much. We're going to revise it again and again, and then for x and x's domain, if x and y, if we choose x in for x, if we choose x and something from x's domain, and if it is leaves nothing for y, and it does not satisfy the constraint x y, we delete x from the x's domain. Domain spelling is wrong. And then revised equals true, else revised equals true, and then we have to return revised. Now for a lot of arcs, that is like in our graph, that is here, this, we have a lot of arc consistency we need here, right guys? We need a lot of arc consistency here. We need a lot of arc consistency here. So for that, we have a little bit of difference in the code. It goes something like this. Function a arc3 ac.ac3, and then CSP, that is constraint satisfaction problem. Then we are going to have q in this, right? Then we are going to have a q in this, queue all arcs in CSP. Okay, we are going to queue all the arcs in CSP. All arcs in the CSP, and while we are going to start a while loop while the queue uh, is non-empty non-empty, then x comma y equals dq. uh, dq means we are going to remove some things because we have a lot of arcs, so we need to remove some things, and then later if we are wrong we may need to add some things, right? So right now we are like going to remove uh, a value from the domain x comma y. We're going to assign that uh, and dq from our queue. Okay, and if then we are going to do that arc one again. If revise CSP, we are going to copy that, have some space, yeah. If size of x domain equals 0, okay, it is equal, but x we are, if the domain comes to 0, right, like we are performing arcs, but if it leaves nothing for the third one, if the domain comes out to be 0, then it is wrong. We are because it is not binary, so if it is not going to be the same. The logic is same, but right now we have done it for two things, for two variables, and then for the third one which is connected with them, and to make that arc consistent with those two, if the domains come out to be 0, then you have to return false, right? So I'm going to write it for that. So we are going to start with if revise uh, CSP comma x comma y, uh, if size of domain, right, if size of access domain uh, equals to false, uh, then we are going to return false. Okay, then we are going to return false. Now we are going to start a for loop again, just here, and we're going to write for each z, z should be capital because we are talking about the variable in access domain, access neighbor y, because we are making it more than making it arc consistent for more than 3, so I have to include this z here too, right? Neighbor in access neighbor, that is curly brackets, so y, capital Y. We are going to now we are going to add things. Okay, now we are going to add that enqueue. Now we are going to use the enqueue function, enqueue, and then q comma z comma x, and then we are going to close, and then we are going to return true. It should be below if. Okay, the orientation matters. Return true. It is under the if, and this is it for multiple arcs. Did you understand the code? Do you guys understand the code? It is not that tough. It is actually not that different too. We just needed to check it for two variables now, and we needed to just add things that need to check if the domain becomes zero, uh, to return false, and if it did not, and later all the things work, then we are going to return true. So that is the thing in this code. Okay, and now that we know all this, we wanna like sometimes using AC3 can reduce domain to make it easier to find, but it will not always find solution. Yeah, that is the thing with AC3. It can reduce the domain, but it will sometimes not give the whole solution. So after that, we may need to do search. Search, if you know, we did in lecture 0. So we are going to frame that. We are going to frame search as a CSP search CSP. Okay, CSP constraint search problem as search problems. So what was the first thing in search problem? That was initial state. Initial state. So the initial state will be empty, of course. Empty assignment. Uh, Empty assignment. No variables. And then the what is the second thing in search problem? Those were actions. And what actions do we perform in CSP? That is adding, right? We add some value to the variable. Add a like a variable equals value to assignment. So now our empty assignment with no variables are empty. Then we need some transition model, of course. So here the transition model can like show how adding an assignment changes the assignment. Like for other things, let me yeah. So our transition model can show uh, how adding an assignment how adding an assignment changes the assignment. Okay, and then we are going to perform some goal test, of course. uh, what was the goal test? To check if we have done everything. So here we will check if uh, all variables are assigned and constraints are satisfied. Check if all variables are assigned and all constraints, of course, are satisfied. And then path cost, because if you remember from the start of the session, I told you path cost it does not matter in optimization, in this type of optimization, because all the path cost have the same cost. Okay, we just care about the solution. Like in the lecture one, like in the exam one, we do not care about the path cost. There is no path cost like that. So all paths have same cost. This may also be written in the PPT, I'm realizing. Constraint graph. Let it load. Yeah. Types of constraint, I've already discussed. Node consistency is good. Arc consistency we have discussed. The revised algorithm we have already discussed. AC3 we have already discussed. CSP is the problem we are on right now, right? We have already discussed this now. Now, yeah. Now this is very important. So backtracking we are not going to discuss. If a variable has first check completion. If a variable has been assigned, return the complete assignment as the solution. Not visible. Okay. So check completion. If every variable has been assigned, return the complete assignment as a solution. If not, like select any unassigned variable, then try each value in its domain in order, like Monday, Tuesday, Wednesday. Then assign if consistent, if it satisfies the constraints, then we are going to go deeper. And then backtrack on failure. If recursion fails, then we are going to undo the assignment and try the next value. If the value fails, then we return failure. So like if we were going like here, like we assigned Monday and then we assigned Monday here. Like we are going in order, right? We assigned Monday here. Okay, no problem. Monday here, constraint does not satisfy. We return failure. We do Tuesday, no problem. Then we come here, we try Monday, no problem. And then let's say this is also connected. And then we say then we try this one. Let's say Monday does not satisfy two constraints. Then we try Tuesday. Tuesday does not satisfy this constraint. And then we try Wednesday, and then it satisfies all constraint. We have done everything, but checking different things. Like, what if we have to go one step back? We have to backtrack. So we are going to understand backtrack now. So backtrack, we are going to understand the code first. This was basically what I told you. Backtrack, like going. If we are wrong, we just go back. If we are error, change something and then try again. Okay. So that is basically backtrack. Uh, Now in backtrack, we are going to try the code. The code for backtrack. Now the code for backtrack looks something like this. Uh, Backtrack. Backtrack. Search. Let me first have a look at the session. The session has been for 1 hour 48 minutes. This session will at least go on for, I guess, 20 minutes. I feel like. So hold yourself. So the code looks like this. The code is a little bit longer. Let me try if no, it will not work. Function backtrack, then assignment, of course. Assignments, comma CSP are a problem. If assignment complete, as I told you, then we are going to return. Then we are going to return. Then we are going to return assignment. Then we are going to return the assignment. Sure. And then var equals variable. Okay, var equals selected sorry, selected comma select sorry select dash unassigned assigned spelling unassigned uh, dash var out of the assignment comma csp. Okay, then we are going to start a loop for, because we need to recursively do the backtrack. Okay, for value in domain dash value values, then var comma assignment comma csp comma csp. Then we're going to close this bracket, then this, and then inside for loop, if value consistent, right now we are checking consistency, consistent with assignment, then we are going to add it add var value, whatever the value is, bracket to the assignment, right. I am trying to read this so that you can understand this, right. This is if you will realize, this is the same thing which we just read, right, in the PPT. And then we are going to the result, then we are going to perform this backtrack assignment comma csp sorry, if result not equals to failure, how do I write not equals to, sorry, if result sorry, if result not equal, sorry, not equal to failure, if it is not a failure, then we are going to return the result, then we are going to return the result, and then the thing which we did with other variables. Have I told you inference in this? It will come after backtrack. Okay. So, so then after that we are going to remove the other var equal to value from assignment. Then we are going to remove var equal to value from assignment, of course, and then if nothing happens, then we are going to just return failure, that there is no solution. Okay, is this that or that? I think so like this, right? Then this is the code for backtrack search. Nothing too out of the extraordinary. Uh, so now when I said I like this, when I said I like this, now is the part that comes that I like. Backtracking action, maintaining our consistency, minimum remaining values, heuristic degree, least constraining value. This is all, right? Degree, highest degree, these are the inference and all. This was the code. The remove has to be outside and the return has to be the inside, okay? Now let me get here, and if you remember I told you that we will come back to this page. Then I said the truth, and let us continue with this page. So we know it could be Monday, Tuesday, Wednesday. Let's say we give this a Monday, and then we can be Monday does not work, Tuesday. Then Monday does not work. Sorry, Monday works. Monday works, guys. Monday works. Now, Monday does not work. Tuesday also does not work. So Wednesday works. Now see, Monday does not work. Tuesday also does not work. And Wednesday also does not work. So it means we need to backtrack. Now we are going to use backtrack in this case. So we are going to remove, and then before E we came, so before C we came to E, but there was only one value possible for E, then it means there was something wrong before E. So before E we were at D, so D was wrong. Tuesday we cannot do. Monday we know is wrong. Monday we know is wrong. So let us try Wednesday. Then Monday works, and then Monday here does not work. Tuesday does not work, and Wednesday this time works. Now let's go to F. Monday does not work. Tuesday works. Now here Monday does not work. Tuesday does not work, and Wednesday works. Now everything is done. It is all the value are assigned, and all the things are assigned. The constraint satisfy, and that is done. Okay. Now we did this using using the sorry backtrack, right? Now there is another other ways we can do this too. One is through inference, right? Now we are going to add inference, through this, and we are going to do everything again, but in a different way. Now it is not done. There are many ways we can solve this, right? We are going to discuss all of the ways one by one. No need of the PPT. Now let's say we took this as Monday, and we took this as Tuesday because Monday does not work. You have to go in order. Monday does not work. Now instead of going to D, we see C. We do our consistency and only Wednesday is left. Okay. Now we see Tuesday, Wednesday, only are connected to E. Only Monday is left. Monday, Tuesday, D is left. There's two our consistency, Wednesday. Now Monday, Wednesday, only Tuesday is left. Tuesday, Monday, only Wednesday is left. Done. No back, even backtrack was not needed. Right? We just did it by maintaining our consistency. So easy, right? So easy. Now there are other ways to do this too. Those other ways are it's not working. Yeah. Now those other ways work like this. Let me check which is the next way actually. Minimum remaining values. Okay. Minimum remaining values we have to do and the heuristic degree we have to do. Okay, these are two ways. And the least constraining value is only left. Okay. Minimum remaining values. For that we need to maintain the domain, which I don't like doing, but we have to do it, right? Let us start with Monday. Now Tuesday, Wednesday are in option. Tuesday, Wednesday are in option. Monday, 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 Tuesday, Wednesday are in option. So two of them. So let's say we chose Tuesday. Now it means Tuesday. So we need to remove this. We need to remove Tuesday from here. We need to remove Tuesday from here. Two are left. One is left. So we assign Wednesday. It is the only value left in the domain. It satisfies everything. So we need to remove Wednesday from here, and we need to remove Wednesday from here. So one here, two here, three here. One here. So Monday assigned. So Monday have to remove from here, from here, from here. One here, two here. So we can assign it Wednesday, we can assign it Tuesday. When we assign it Tuesday, Tuesday gone, Wednesday left, and done. So we were checking which has the least value left in its domain, and then we assign it to that. But if but there can be some problem in this too. We are going to discuss that in a minute. Before that, we discuss the problem. We are going to end it with a heuristic degree. If you notice, we are always starting from A. Who bounded us to start from A? No one. We can start from B. We can start from C. We can start from D. Right? So we are going to do this. Now we are going to get bounded, and we are going to start with the one which is connected to the most nodes, and we can see E is connected to the most nodes. So we are going to start with E. So let's say we started with E as Monday, so we made D Tuesday, then this become Wednesday, and then let's say this become Tuesday, this became Wednesday. I'm using our consistency. Monday, Tuesday, this become Wednesday, and Monday, Wednesday, this become Tuesday. Everything is followed, everything happened, but this time we said, let's do the one which is connected with most. Okay, right. Now we are going to do. Now we are going to get in the problem. For that we need to look at the code. You see here, I have not actually told you how this domain values work. How this domain values work and how this select select unassigned var works. I have not told you that till now. So before we get into the problem, actually let us first see this select unassigned. No, the problem is in the select unassigned. How are we selecting? So minimum remaining values, that is the MRV. Sorry, we are using white, that's why it is not visible. MRV, minimum uh, minimum remaining values you stick. Select the which means select in which we select the variable that has the smallest domain. Okay, but in degree heuristic we select, but in degree heuristic, this was the one which we were doing before, right? The smallest domain we were using. But there is another way. Problem is degree heuristic. Degree heuristic. In that we select the variable that has the highest degree. Why do we do that? Because we have then more values of combinations, more combinations left to assign different values to. If we do the one with the lower ones, we have more risk of doing backtracking. Like we have to do backtracking because we are making our different what do you say? Our different values are like different possible outcomes are becoming lower and lower. Okay, there's no differentiation there, right? So here I know I'm going up against this MRV, uh, but this can sometimes help, right? Degree heuristic. We are not going to try degree heuristic. You can try it on. I've already explained you what is degree heuristic. Degree heuristic is when we select the variable that has the highest degree. You can try it on your own. Okay. Now uh, let us try understand how does this domain values work. That's the last thing which we are going to understand, and then we are going to do the recap and then the bias. Okay, how does this domain value work? uh, this domain value so can, in this domain value we can use the least constraining value heuristic. We can use the least uh, constraining training value heuristic. In this we return the variable in order by number of choices that are ruled out by neighboring variables. That is, we are returning variables in order by uh, number of choice that are ruled out by neighboring variables. That is very close to maintaining arc consistency. But we are going to return variables in order by number of choices, right? In which we have the least constraints. Okay. So in this we try learning constraining value first. In try learn we do constraining values first, and in least constraining value heuristic we do the least constraining value first. Okay, this is how the domain value picking works. So this is how the least constraining value works. Now let us get into the PPT, because we don't want to miss anything, right? here's the PPT, heuristic degree, the least constraining value. When assigning a value to a variable, we choose the one that rules out the fewest values. Okay, that is the least constraining value in neighboring domains. The least constraining value is CLV heuristic. This preserves flexibility in other variables and reducing the need to backtrack, which I have already told you. This is recap. Uh, Instead of using this as the recap, uh, so the recap goes like this. Today we learned three categories of problems: local search, linear programming, and the CSP, that is the constraint satisfaction problem. In local search, we learned about hill climbing, the problem in hill climbing, and then how we solve it through simulated annealing. We learned the different variants of hill climb, how hill climbing works, the squid, and then the simulated annealing. How does that work? We learned the code for hill climbing and the simulated annealing. Then in linear programming, we learned optimizing a linear cost function with linear constraints via simplex or interior point, or using the SciPy optimized linprog, which is best for continuous variables with structured constraints. Okay, and then we spend a lot of time in this constraint satisfaction, that is the CSP, which is defined by three components, that is the variables, domains, and constraints. And the constraints are of two types, that is hard and soft, and inside them we have unary and binary constraints. Then maintaining unary constraint, we had the node consistency, and maintaining the binary constraints, we had the arc consistency. And then we revised it into the AC3, in which we had more than two arc variables. And then we learned about backtracking and inference, that is and exploring the solution efficiently. And then we learned about some heuristic, that is the MRP, the degree, and the LCV, making backtracking significantly faster by guiding variables and value selection. If we select the value very precisely and with a lot of knowledge, then we it is backtracking does not need to happen again and again, right? You don't need to perform same thing again and again, run the code again and again, the loop again and again. So this makes it significantly faster. So this was today's session on optimization. Tomorrow we do not have our session, but our next section is very important, which is on machine learning, a very important part. So if you like today's session, subscribe, like, and comment. Right. Thank you for the support, guys. I'm going to see you soon on probably day after tomorrow. We are going to decide on that. Uh, you can check out our search, knowledge, and probability lectures too. Hope you like today's session, and you can of course comment for more things, more other uh, things which we did not include. Maybe we made some mistake, or maybe you want to correct us, or you want to do something like more. You want to suggest some improvement. We are open to that. So see you soon. See that the lecture still we are not present. Uh, so bye guys. I hope you like today's lecture. See you soon.